Welcome back in lecture series on topic chemical thermodynamics. In last lecture, we have studied what is meant by spontaneous process and energy relation between energy and spontaneity. And in that lecture, we have studied that spontaneous reactions takes place in a direction in which energy of the system is lower. That means energy is released during the reaction. That means those reactions which are exothermic, that are spontaneous, or in other words, spontaneous reactions are exothermic in nature. But it is not always true. There are some reactions in which energy is absorbed, and though energy is absorbed, these reactions are spontaneous. That means energy only cannot decide whether the reaction is spontaneous or non-spontaneous. That means from energy absorbed or energy released, we cannot decide whether the reaction is spontaneous or non-spontaneous. And therefore, we have to consider the another thermodynamic factor that decides the spontaneity of the reaction. And that factor is entropy, which decides the spontaneity of the reaction. And today, in this lecture, we will learn what is meant by entropy and how it is measured. So, entropy is a measure of molecular disorder or randomness during the chemical reaction, produced during the chemical reaction, that is called as entropy, and is denoted by letter capital S. Now consider here an example, that is melting of ice. Solid ice is there, and when solid ice melts, in solid ice the arrangement of the molecule is in ordered fashion. Molecules are arranged in a definite order. When it melts, when it absorbs heat from the surrounding, it melts, and when it melts, it gets converted into liquid state. And in liquid state, the arrangement, the definite ordered arrangement is disturbed, and it goes into the liquid state. The bonding between water and water molecule breaks. And when the liquid is converted into water vapors, then these molecules inside the water molecules, they can freely move in the available space. So randomness or molecular disorder is increased. So if you observe the molecular disorder or in all these three cases, then in solid state molecules are in a highly ordered state, and when it melts, the highly ordered state get converted into disordered state. And here in water vapors or in the gaseous water, highly disordered state is formed. So entropy increases during this change from solid to liquid and liquid to gas, because entropy is a measure of molecular disorder or randomness. Now see here in detail. So in solid ice, arrangement is like this. Molecules are arranged in a definite pattern, definite fashion. Ordered arrangement is there. When it melts, then this order arrangement, it gets converted into liquid water, and the order arrangement is disturbed, changed, and molecules are free to move within the liquid. And as the bonding between the water molecules becomes weak, the molecules can free to move within the liquid. And when that means disordered state is formed, and when it is heated, then it gets converted into gaseous state. And in gaseous state, water molecules are free to move in random direction, and in the available space they can move anywhere. They move away or they goes away from each other. as force of attraction between the molecule is less, very, very less or negligible. So in gaseous state, water molecules are they can freely move in random direction, and therefore the highly disordered state is formed. Thus, during this conversion from solid ice to water, gaseous water molecules, highly disordered state gets converted into highly disordered state. That means randomness is increased, molecular disorder is increased, and therefore entropy increases during this change. During the whole change, entropy of the system increases. Now suppose here S1 is the entropy of solid ice and S2 is the entropy of liquid water. Then the S2 minus S1, that is entropy of final state minus entropy of initial state, gives you change in entropy. Or suppose entropy of gaseous water is S3, then S3 minus S2 is equal to delta S, and this delta S means change in entropy, and this change in entropy may be positive, may be negative, or may be zero. If the entropy of final state is more than initial state, then delta S is positive. That means if the entropy of product is more than entropy of reactant, then delta S is positive. But if entropy of reactant is more than entropy of product, then delta S is negative. And when entropy of both product and reactant is same, then delta S is equal to 0. So remember that when delta S is positive, when entropy of product, that means randomness of product or molecular disorder of product is more than molecular disorder produced in the reactant, then delta S is positive. When the molecular disorder produced in reactant is more than product, then delta S is negative, and molecular disorder or randomness produced in reactant and product is same, then delta S is 0. So during melting of ice, we have studied that, or in vaporization of liquid, the randomness or disorder increases and therefore entropy increases. That means what? If randomness is less, entropy is less, and randomness is more, entropy is more. So when during the conversion of solid state into gaseous state, randomness goes on increasing, and therefore the entropy goes on increasing. So therefore when solid is converted into liquid, delta S, that is entropy change, is more than 0, and when liquid is converted into gaseous state, entropy change is still more than or greater than 0. So greater the disorder of a system, larger is the entropy. So we will see here some examples. Consider here a dissolution of solid in iodine in water. Now solid iodine has less entropy because molecules are arranged in a definite fashion. But when it is dissolved in water, then this arrangement is disturbed. It gets dissolved, molecule gets separated, and therefore gets solvated or hydrated, and therefore what happens? The entropy increases. The entropy of iodine in aqueous state is greater than entropy of iodine in a solid state, and therefore delta S is positive in this example. Another example, consider a dissociation of hydrogen molecule into atoms. Now hydrogen molecule in a gaseous state, in hydrogen molecule two hydrogen atoms are bonded by each by covalent bond. A bond is present between two hydrogen atoms. When it dissociates, then two separate hydrogen atoms are formed in a gaseous state. Here both reactant and products are in a gaseous state. But what is the difference? Here reactant is in a molecular state and gas product is in a atomic state. So here in this molecule, two hydrogen atoms are bonded, and when this bond breaks, then two hydrogen atoms are formed. Separate hydrogen atoms are formed. So randomness is more in case of atoms than in case of molecule. So here as randomness is increased, delta S is positive. Now try some other examples and find out whether the delta S is positive or negative or zero. Try this. This is the reaction. So by observing the reaction, you can say that whether delta S is positive or negative. Now here in reactant side, 2 moles of hydrogen gas are there and 1 mole of oxygen gas are there. So in the 3 moles of gaseous reactants are there, and here 2 moles of gaseous liquid products are there. Or product is in a liquid state. 2 moles of water in the liquid states are there. So here if you calculate the delta S, that is change in entropy, by using the equation that is entropy of product minus entropy of reactant, then the entropy of product is less than entropy of the reactant. So here delta S is negative because here both reactants are in a gaseous state and product is in a liquid state. Here 2 moles of water are formed. Number of moles of water are 2 and that are in a liquid state. And here the number of moles of reactants are 3 and all these are in a gaseous state. Therefore, entropy or disorder of reactant is more than disorder produced in the water, liquid water, and therefore delta S is negative. Or another example, that is calcium carbonate. Here it is in a solid state. When it decomposes, it gives calcium oxide and carbon dioxide. Calcium carbonate is in a solid state, so entropy is less as it is in a solid state. But when it gets converted into calcium oxide and carbon dioxide is evolved, carbon dioxide is in a gaseous state, so entropy is more, randomness is more, or disorder produces more, and therefore delta S, therefore the entropy of product is more than entropy of reactant, and therefore delta S is positive. So like this you can solve the example based on entropy. Now, entropy is a state function. Entropy is state function, that means it depends on initial and final state of the system. When system changes from one state to another state. And from that we can calculate the change in entropy. Entropy change is generally represented by delta S. And delta S is equal to entropy of final state minus entropy of initial state. Or delta S is equal to entropy, total entropy of products minus total entropy of reactant. That will give you the change in entropy. So like this you can calculate the change in entropy. And entropy is an extensive property. It depends upon the amount of the substance present in the reaction. So it is an extensive property. Remember that entropy is a state function. It depends upon initial and final state of the system, and change in entropy is calculated by using this equation, that is entropy of product minus entropy of reactants, and entropy is a extensive property. All these are the important point concerned with the entropy that you must have to remember. Now quantitative definition of entropy or mathematical expression for entropy. So an entropy change of a system is equal to amount of heat transfer to the system in a reversible manner divided by the temperature in Kelvin at which the heat transfer takes place. That is the definition of entropy, quantitative definition of entropy. And according to this definition, delta S is equal to Q reversible divided by T. But you know that heat is expressed in joules and temperature is expressed in Kelvin. So unit of delta S, that is change in entropy, is joules per Kelvin. Remember that unit of delta S means change in entropy, is expressed in joules per Kelvin. So when heat is added to the system, then kinetic energy of the particles in the system increases. Therefore, molecular motions increases. And when molecular motion increases, molecular disorder increases. And when molecular disorder increases, entropy also increases. So, when heat is added to the system, entropy of the system increases. And therefore, delta S is directly proportional to heat added to the system in a reversible manner, Q reversible. So delta S is proportional to Q reversible. And this heat added depends upon the temperature. The effectiveness of the addition of heat to increase randomness or to increase the disorder, that depends on the temperature. That means what? If the system is already at low temperature, if the temperature of the system is low and certain amount of heat is added to such a system, then disorder caused is more, disorder produces more. That means what? If a silent place is there, and in that place if someone sneezes, then whatever disturbance produces more. But if system has high temperature, already system is at high temperature, and the same amount of heat is added to such a system, then disorder caused is less. Whatever disorder produced is less. That means if a bus station is there, a railway station is there, and in that railway station a noisy place is there, and in that someone sneezes, then the disturbance produces less. So the same amount of heat is added to the system which is at high temperature, then disorder cause is less. So delta S therefore is inversely proportional to the temperature at which the heat is added. So delta S, that is change in entropy, depends upon the temperature also, and it is inversely proportional to temperature. If heat is added to a system at high temperature, the disorder created is less. But if the same amount of heat is added to the system at low temperature, then disorder produces more. So I hope that you understood this point, and thank you.